Hello, this is Richard Hammack's Calculus 1 course. We're in part 5 of the course on integration. In fact, we're at the very end of part 5 and at the end of the course. Lecture 46 is our final lecture. We'll do a couple of things in this brief lecture. To begin, we've recently been talking about the substitution rule for finding indefinite integrals. We'll ponder the question, what if substitution does not work? Then we'll summarize the course and take a brief look ahead. So on to that first question, what if substitution doesn't work? It's easy in a first course in calculus to come away with the false impression that we can find the indefinite integral of just about any function we see. And you can legitimately think this because all of the exercises you work in the book are integrals that you can do. But it's a fact that most functions you could write down, you'd have a very hard time finding the integrals of. Substitution has greatly expanded the kinds of integrals we can find, but it's not a silver bullet. First of all, it's a very fragile method. A couple of things have to happen before you can apply substitution. First of all, for substitution to work, the integral must have the form integral of f of g of x times g prime of x dx, so that you can make the substitution u equals g of x, and so du will be g prime of x dx, and you reduce it to a simpler integral. So first of all, it has to have this form. But secondly, once you've made the substitution, you need to be able to find the integral of f of u du. And if either one of those is not the case, substitution is not going to work. So there are a ton of problems we can't do by any method. To give a really simple one, how about the integral of secant x dx? That's a function whose derivative is secant x. And you may not be able to think of one, and none of our rules apply. Consider also the integral of cosine of x cubed times x cubed dx. Your first impulse is to make a substitution, u equals x cubed, but then du would be 3x squared dx. And the 3 is okay, we can deal with that. But look, we need an x squared, and we've got a x cubed right here. And you can try all day, but you're not going to be able to overcome that. Well, actually you can, and you will later if you go on to calculus 2, but it's not obvious how to do it. For another problem, how about this simple integral, the integral of ln x dx? That would be a function whose derivative is ln x. And it's hard to think of one. So these are just a few examples of integrals we can't do. But if you go on to calculus 2, you'll be able to do them. A lot of what you do in calculus 2 will build on what we've done here. In fact, all of it will build on what we've done in calculus 1. In particular, one of the things you'll do in calculus 2 is work with integrals of more functions than you can currently deal with. Here's another integral that's problematic, at least on first brush. The integral of cosine squared x dx. What is it? If it were the integral of cosine x dx, of course we could do that. But the square presents a problem. The same thing with the integral of sine squared x dx. It's hard to say what that would be. You can try substitution, you can hunt through your list of integration rules, but nothing's going to apply. You're probably going to have a problem with this. But I want to illustrate on this page that sometimes, especially with trigonometric integrals like this one that are problematic, a trig identity can come to your rescue. And in fact, if you think way back to the first part of this course when we were doing our trig review, we had an identity involving cosine squared x and another involving sine squared x, an identity that expressed each of those in terms of linear terms. Here they are. Remember this one? Cosine squared x equals 1 plus cosine 2x over 2. And sine squared x equals 1 minus cosine 2x over 2. These two identities are really useful because they convert squared trig functions, sine and cosine, to expressions where nothing is squared. And when you're doing integrals, sometimes squares can mess you up. It's a fact, especially if you go on to Calc 2 and 3, you're going to see a lot of integrals involving sine squared and cosine squared, and you're going to need to know how to do them. And the way you can handle those, or one way, is to use these trig identities. For example, let's work out the integral of cosine squared x dx, using the fact that it's equal to this expression. That would give us the integral of 1 plus cosine 2x over 2 dx. And we can take out the 1/2 constant multiple. You get 1/2 times the integral of 1 plus cosine 2x dx. And look, this is easy because we can find the integral of 1. It's just x. And what about the integral of cosine 2x? We can find that with substitution. In fact, you can really do it in your head at this point. You get 1/2 x plus, and then the integral of cosine 2x is 1/2 sine 2x. And then plus the ubiquitous c. So there we go. That's our answer. You can clean that up a little bit as x over 2 plus 1/4 sine 2x plus c. See how easy that was with just a trigonometric identity applied? This can often help integrals with trig functions. If you're unsure about this, you can check it. You can differentiate your answer, and let's see if we get cosine squared x back. Using familiar derivative rules, we get 1/2 plus 1/4 cosine 2x times 2, and that simplifies to 1 plus cosine 2x over 2, and that's cosine squared x. So we differentiated the answer, we got our integrand back, so we did it right. It checks back. So you may want to try some exercises like this in the text, just to stretch your mind a bit. Be on the alert for them, this kind of problem and this technique, especially if you move on to Calculus 2. So that's it. Speaking of Calculus 2, we've reached the end of Calculus 1. And I want to give you an overview of what we've learned, and we've learned a lot in this course. First of all, we tackled limits, and we needed those for slopes of tangent lines. And we learned how to compute limits, and from them, we defined the fundamental concept of the derivative of a function. Then we learned rules for differentiation that allowed us to bypass the limit. The product rule, quotient rule, chain rule, and so on. A lot went into that. And then we looked at applications of differentiation, like max-min, Newton's method, L'Hopital's rule, and so on. We've learned about indefinite integrals, which are derivatives in reverse. The integral of f of x dx equals big F of x plus c just means that the derivative of big F of x plus c equals little f of x. We call this an antiderivative of little f of x. And we came up with lots of rules for integration. Every time we had a differentiation rule, we got an integration rule for free. We moved on to definite integrals. The integral from a to b f of x dx is equal to this limit of Riemann sums. We looked at their properties, and then we learned about the fundamental theorem of calculus that says this definite integral, this limit, finding it is as simple as finding an antiderivative for the integrand. And we looked at lots of applications of that. In conclusion, I want to say that if you're moving on to other disciplines at this point that may use calculus, whether it's Calculus 2 or some other scientific discipline, pay close attention to these limits for the derivative and also for the definite integral. Because what you'll see time and time again in applications of calculus is you'll model a problem, collecting data about the problem and analyzing it, and putting it into a mathematical formulation. And that formulation will likely, in many cases, involve a limit that suddenly looks like the limit of Riemann sums. It may come into focus as something like this. And knowing the definition of a definite integral tells you that's a definite integral. And as soon as you know that, you can do calculus with that. It's the same with the limit definition of a derivative. These limit definitions give the objects of study in calculus their meanings, and they make it useful. So that's it for Calculus 1. I hope you found these lectures useful. They were certainly fun to make. And I wish you the best of luck in all your future endeavors. Goodbye.